Many people are familiar with miniature circuit breakers, MCBs, which we use in residential and commercial distribution panels. But when an installation requires higher currents or needs to withstand larger short circuit levels, that's when the MCCB, molded case circuit breaker, comes into play. In this video, you will understand what an MCCB, molded case circuit breaker, is, why it has this name, and what the main differences are between it and the miniature circuit breaker, MCB. The MCCB gets its name from its physical structure. The housing material is usually made of heat-resistant and flame-retardant thermosetting plastic. It offers high impact resistance, making it ideal for industrial and commercial applications. Its rated current is high, and it is used in circuits that demand larger currents. Many people have questions about MCCBs, mainly about the difference between an MCCB and an MCB, and in which situations an MCB or an MCCB should be used. Miniature circuit breakers, MCBs. These are the most common in residential and commercial installations and typically have rated currents from 1 ampere up to 125 amps, short circuit breaking capacities of up to 10 kiloamps, 10,000 amperes. Molded case circuit breakers, MCCBs. These are used in industrial installations and have rated currents that can reach up to 1,600 amps. Short circuit capacities ranging from 65 kiloamps to 100 kiloamps, meaning 65,000 or even 100,000 amperes. Another difference is in the switching mechanism. MCBs have only two handle positions, up, on, and down, off. MCCBs, on the other hand, have three positions, up, on, down, off, and a center position. This center position indicates that the breaker has tripped due to a short circuit or overload. So with this type of breaker, when a fault occurs, you can identify it by the position of the handle. In addition, MCCBs have a test button. When pressed, it checks the mechanism and the handle also moves to the center position. With the rated current and short circuit capacity of an MCCB, it becomes clear that choosing between an MCB and an MCCB depends on these values and on the requirements of the electrical installation. For example, if you have a circuit where the rated current exceeds 125 amps, the MCB will not be sufficient. In this case, using an MCCB is mandatory, as it can handle much higher currents. Another important point is the short circuit current. Let's imagine you have an MCB with a 6 kiloamp short circuit rating, but your installation has a prospective short circuit current of 15 kiloamps. In this case, even if the MCB manages to interrupt the circuit, it may explode or suffer severe damage because it was not designed to withstand that level of short circuit current. In this scenario, an MCCB must be used. It's also important to mention that you may need an MCCB even when the rated current is below 125 amps, even though MCBs with the same current rating exist. For example, there is a three-phase 100 ampere MCB, and there is also a three-phase 100 ampere MCCB. However, if the short circuit current at that distribution panel exceeds 10 kiloamperes, you must use an MCCB with a short circuit capacity above 10 kiloamperes. Here is an example of two breakers, both rated at 100 amperes. One MCB with a 3,000 ampere short circuit rating and one MCCB with a 25,000 ampere short circuit rating. Now let's understand how the MCCB, molded case circuit breaker, works. We'll start with the MCCB terminals, which are the points where the cables are connected. These terminals are made of metal plates, and the cables are connected using a ring-type terminal, lug. The nut located at the bottom of the plate is used to secure the screw that tightens the terminal. This metal plate is where the cables leave toward the circuits. In this region, we also find the bimetallic element that trips the breaker in case of overload, as well as the mechanism that trips the breaker in case of a short circuit. On the front part of the breaker, we have the moving contacts, which open and close the circuit. This is the point where the supply cables arrive, and above these plates is the arc-extinguishing chamber. I'm going to show you the assembly of the mechanical part of the handle. In this mechanical section, where the MCCB handle is located, I will leave the contacts opening and closing, so you can see the pieces moving. The contacts close with significant pressure because of these two springs. When the handle moves forward to turn the breaker on, this mechanism shifts forward and closes the contacts. Now that you've seen how the handle components move, it's easier to understand how the MCCB turns the circuit on and off. Earlier, I showed you that one of the differences between an MCCB and a miniature circuit breaker, MCB, is exactly this handle mechanism. While an MCB has only 2 positions, the MCCB has 3, and the center position is where the breaker stays when it trips due to a short circuit or overload. So let's understand how the handle stays in this center position. Inside the MCCB, there is this movable part located behind the handle. This piece moves forward when there is an overload or short circuit. It activates the mechanical system of the breaker, releasing a latch that was locked in place, causing the contacts to open and the handle to move to the center position. To reset the breaker, you must first return the handle to the off position. At that moment, the latch locks back into place, and the breaker can be turned on normally. Another important component is the arc-extinguishing chamber. MCCBs have much larger arc chambers than MCBs, and that's why they can handle much higher short-circuit currents. Here we have 2 examples. A chamber from an MCB with a 3,000 ampere short-circuit capacity, and a chamber from an MCCB with a 50,000 ampere capacity. This arc-extinguishing chamber is positioned right in front of the moving contacts and is responsible for extinguishing the electrical arc when a short circuit occurs. With this internal functioning of the MCCB, it becomes clear why it has a much larger structure than an MCB. It not only offers greater mechanical and electrical strength, but also provides much more robust protection for installations that operate with higher rated currents and short-circuit levels. And that is exactly why MCCBs are widely used in industrial applications and distribution panels. See you in the next video, everyone.